All right, let's talk about a force that is literally everywhere. From the souvenir magnet holding up a picture on your fridge, all the way up to the invisible shield protecting our entire planet. We're talking about magnetism. And in this explainer, we're going to trace its story from a simple, mysterious rock right up to the physics that powers the phone in your hand. Let's dive in. So here's the game plan. First, we're going to get to know magnets themselves. Then, we'll see how a jolt of electricity blew the lid off its secret connection to magnetism. After that, we'll learn how to map these invisible forces, watch how they can steer tiny particles, and finally, see how all this knowledge led to some of the most critical tech we use every single day.
Okay, let's start at square one, the world of magnets. We're talking about the absolute basics here, the kind of simple magnet you probably played with as a kid. You might have heard it called a lodestone, or, as it's called in some of our sources, a calamita.
So what even is a magnet? Well, at its core, it's just an object that creates an invisible force field around itself. And the one non-negotiable rule is this. Every single magnet, whether it's a tiny metal shaving or an entire planet, has two poles, a north and a south. They are, as we're about to see, inseparable partners.
And this is where magnetism gets really, really weird compared to electricity. See, with electricity, you can have a positive charge just floating around on its own, no problem. Same with the negative one. But magnetism, no way. If you try to isolate a north pole, you will fail every single time. If you snap a bar magnet in half, hoping to get a separate north and south piece, you don't. You just get two brand new, smaller magnets, and guess what? Each one has its own north and south pole. It's a fundamental rule of the universe that makes magnetism totally unique.
So how in the world do you map a force you can't even see? Well, scientists came up with this brilliant idea of a magnetic field, which we draw using what are called lines of magnetic field. Just think of them as invisible highways. They always flow out of the North Pole, loop all the way around, and then re-enter at the South Pole. And they trace the exact path a tiny compass needle would follow if you placed it anywhere along that highway.
For centuries, people thought electricity and magnetism were two completely different things. They had nothing to do with each other. But then, in 1820, a physicist named Hans Christian Ørsted was in the middle of a lecture and just happened to stumble upon a connection that would completely rewrite physics.
As the story goes, he was just setting up a demonstration, and he noticed something odd. And it all came down to this simple, powerful question. What happens when you run an electric current through a wire that's right next to a compass? The answer was about to turn everything we thought we knew on its head. The experiment itself was almost laughably simple. You have a wire, you have a compass. With no electricity, the compass does what it always does. It points north. But the instant you flip the switch and a current starts flowing through that wire, the needle jerks sideways, pointing in a totally new direction. The conclusion was just inescapable. A moving electric charge, a current, doesn't just do electrical things. It actually creates its own magnetic field. The two forces weren't separate at all. They were linked.
Almost immediately after Ørsted's discovery, a guy named André-Marie Ampère came along and gave it some mathematical muscle. He formulated what we now call Ampere's law, which essentially became the instruction manual. For the very first time, we had a way to precisely calculate the strength and shape of a magnetic field created by any electric current. This, right here, was the real birth of electromagnetism.
Okay, so we've established that currents create magnetic fields. But what do they look like? What shape do they have? Well, as scientists like Biot and Savart figured out, it turns out the shape of the wire is everything.
Let's start with the simplest case, a long, straight wire carrying a current. The magnetic field it creates forms these perfect concentric circles all around the wire. And there's this really cool trick to figure out which way the field is pointing, called the right-hand rule. You literally point the thumb of your right hand in the same direction as the current, and your fingers will naturally curl in the exact direction of the magnetic field. A simple, physical rule for a totally invisible force. All right, so what if we take that straight wire and bend it into a circle? A loop. Well, now something really neat happens. All of those circular field lines suddenly get funneled together and concentrated right through the middle of the loop. The effect gets amplified, and all of a sudden this simple loop of wire starts acting exactly like a tiny flat little magnet with its own clear north and south face.
Now for the big engineering payoff. If one loop is good,
What about hundreds of loops all wound up into a tight coil? That's what we call a solenoid. Inside this coil, the magnetic field becomes incredibly strong and almost perfectly uniform. And on the outside, it's super weak, almost zero. This ability to create a powerful, focused, controllable field is the secret sauce behind everything from the giant electromagnets in scrapyards to the MRI machine that lets doctors see inside our bodies.
So, up to this point, we've seen that moving charges can create magnetic fields. But you gotta remember, physics is a two-way street. So what happens if we flip the scenario around? What happens when a moving charged particle flies through a pre-existing magnetic field? Well, it turns out, the field pushes back.
And it doesn't just push back, it pushes back in a very specific and kind of weird way. The force is called the Lorentz force, and it's a cornerstone of physics. But here's the twist. It doesn't push the particle forward or slow it down. The force is always perfectly sideways, at a right angle to both the direction the particle is moving and the direction of the magnetic field itself. It's like a constant nudge from the side.
And this constant sideways push creates some truly beautiful motion. If a charged particle enters a magnetic field at a perfect 90-degree angle, that sideways nudge forces it into a perfect circle. But if it enters at any other angle, you get this amazing combination. It moves forward, but it's also being pushed sideways. The result is this elegant corkscrew shape, what physicists call a helical trajectory. And that corkscrew motion, that's not just some abstract thing in a lab. It's happening on a planetary scale above our heads right now. The Earth's magnetic field is like a giant particle trap for dangerous charged particles flying in from the sun. The Lorentz force grabs them and forces them into these enormous helical spirals along the field lines. These spirals are the Van Allen radiation belts, a massive magnetic cocoon that protects all life on Earth from the constant blast of the solar wind.
So once we've finally cracked the code, once we understood how currents create fields and how fields steer charges, we could start building things. We could finally put all this fundamental physics to work, and that unlocked some absolutely incredible technology. Take the mass spectrometer. It's basically a sorting machine for atoms. First, you fire ions into a magnetic field. The Lorentz force kicks in and bends their path. Now here's the genius part. Heavier ions have more inertia, so they resist that turn and make a wide arc. Lighter ions get whipped around into a much tighter curve. By simply having a detector at the end that measures where they hit, you can tell exactly what atoms you're looking at just by separating them by their mass. Or how about the velocity selector? This thing is an incredibly clever filter. It uses both an electric field and a magnetic field, set up at right angles to each other. So as a particle flies in, the electric field pushes it one way, while the magnetic field pushes it the exact opposite way. For any given particle, there is one and only one specific speed where those two opposing forces perfectly cancel each other out, allowing it to sail straight through, completely untouched. Everything else, faster or slower, gets knocked off course. It's a perfect speed filter. But maybe the most common application of all comes from a principle called the Hall effect. And the idea is pretty wild. If you have a current flowing through a wire and you apply a magnetic field to it, you can actually create a tiny measurable voltage across the wire. What's happening is the magnetic field is literally pushing the moving electrons inside the conductor over to one side. That pileup of charge creates a voltage. Now, that tiny voltage, the Hall voltage, it might not sound like much, but it's the core principle behind billions and billions of sensors. Your car's anti-lock brakes use them to measure wheel speed. Your smartphone uses one to know when you've closed its magnetic cover. That small, strange side effect of a magnetic field provides a direct link from mind-bending physics right into the palm of your hand.
So we've journeyed all the way from a simple magnetic rock to a fundamental force that shields our planet and powers pretty much our entire modern world. And it all kicked off because one person, hundreds of years ago, noticed a compass needle twitch. It really makes you wonder, what other invisible connections are out there waiting to be found? What other fundamental forces are still waiting to be unified? Thanks for joining us on The Explainer.